Welcome to this lecture series on programming languages. My name is Oscar Nierstrass and I'm the lecturer for this course. Today I'll give you a quick overview of the schedule of the course. We'll have a look at what programming languages are and what different paradigms are, and I'll give you a quick tour of the history of programming languages in computer science. As I said, my name is Oscar Nierstrass. The assistants for this course are Mohamed Reza Hazarpezant and Joël Niklaus. Most of the material for this course you will find on this web page. Please note that it's important for you to register both on Academia as a JMCS master student and also on Ilias on the University of Bern website for the question and answer forum. Here we see the main web page for this course on our local server with information about the course, and you also find several important links. In particular, there's a link to the Ilias question and answer forum that we can see here. There are the podcasts which are available for download. There are further programming language resources, so articles, questions and answers, downloads, and so on. There are the annotated course slides, the PDFs of all of the presentations with additional hidden slides for your information. There's a Git repository with many of the examples that I'm showing in the presentations. And for bachelor students, there's a link to the KSL page if you need to register there for the final exam. On the Ilias page, you will find in addition to the links that I've mentioned before, the question and answer forum. It's important for you to register on Ilias because we'll be using mainly this web resource to send you messages about everything that's happening with the course, and you can also use it for any questions you have either about the course material or about any administrative aspects of the course. Let's have a closer look at the course schedule. First of all, I'll be using a variety of different sources, so there's no one specific textbook that you need to refer to. One of the ones that I've used is the classic by Loudon, but there are many other textbooks on programming languages which will contain similar material. I'm also using a variety of other articles. For example, this famous article by Hudak is very important for the material that we'll be looking at based on functional languages. I'll be providing links to further sources as we move along in the course. Here's an overview of the course material. Here we are at the introduction. Notice that you do not find any names of any specific programming languages here in the titles of the lectures. That is because in the course we're focusing on programming paradigms and fundamental concepts rather than on specific languages. However, of course, we'll be using specific languages as examples. Next week, for example, we'll be having a look at stack-based programming, and our example language will be PostScript, a language that is usually associated just with printing and with printers, but as we'll see, it's an interesting language on its own from the perspective of the stack-based paradigm. Then we'll continue with functional programming, taking Haskell as an example. We'll dive into the issue of types in programming languages and polymorphisms, continuing with Haskell. Then we'll move back in time and have a look at the lambda calculus and see how the lambda calculus has influenced and is very important for understanding the design and evolution of programming languages in history. We'll have the usual spring break, after which we'll have a look at fixed points, which arise in the lambda calculus, but are also important in the context of programming languages. We will see how not only the syntax of programming languages, but also their semantics can be formally defined, and we'll have a brief lecture having a look at denotational semantics. Then, as most of us are familiar with object-oriented languages, we'll have a look at the object-oriented paradigm, and in particular prototype-based languages which abandon classes in the context of objects. Our example language this time will be JavaScript. Next, we'll dive into a more theoretical lecture where we'll look at the relationship between objects and types and classes, after which we will move to the paradigm of logic programming with Prolog, and follow that up with some examples of how logic programming can be used to solve a variety of different problems. Finally, as the last lecture in the series, we'll do an overview of different kinds of visual programming languages in the history of computer science. The final exam is planned for the 4th of June. If you download the PDFs from the course website, you will find, in addition to the slides that you see in the podcast, some additional hidden slides. They look different, with a different font and a different style to set them apart from the content slides. These slides contain additional information, definitions, explanations, pointers to additional material, and so on. So I encourage you to download the slides and have a look at those. Particularly, you will find them useful in studying for the exam. Before we dive into the question of programming paradigms, let's first take a look at the question, what is a programming language in the first place? I suggest you stop the podcast at this point and take a couple of minutes to think about what programming languages are and how you might define them before continuing with the podcast. So there are quite a few different things that you could take as starting points for defining programming languages. First of all, it's quite clear programming language is a formal language for describing computation. You could also think of it as a user interface to a computer. Or if you want to take a more technical viewpoint, a programming language has a syntax and a semantics, which define what the language is. So the syntax are what textually constitutes valid strings and programs in the language, and the semantics are how you interpret it. Or you could take as a definition whatever the compiler or the interpreter or the translator for the language causes the language to do. Or another way of thinking about it is that a programming language is essentially a tool that supports a particular programming paradigm. Well, you'll find lots of different definitions if you start scraping around in different textbooks and articles on programming languages. Loudon, the textbook that I took as a starting point for this course, he defines it as a notational system for describing computation in a machine-readable and human-readable form. Not a bad definition, so it emphasizes the fact that programming language is a notation. It's something that's written. It's something that helps you describe computation, and both computers are supposed to read it and humans are supposed to read it. So those are some of the key points. My point of view in this course is that a programming language is a tool for developing executable models for a class of problem domains. So stepping back from the purely technical aspect, and I want you to think much more about what kinds of problems can you solve with this given programming language. So if you decide that you are building a web system, a website, or you're implementing a banking system, or you're writing a program to analyze some data, you will choose different languages and you might write your programs in rather different ways. I think that is the aspect which is getting to the core of what programming languages are and why we distinguish between them. So, in this course, we'll be looking at essentially three different high-level aspects. One, what are the different programming language paradigms that support problem solving? So we'll be seeing functional programming and stack-based programming and logic programming and variants of object-oriented programming. Second of all, it's important to understand the foundations of programming languages. So not only syntax, but semantics. Where do programming languages come from? How do we reason about them formally? And finally, semantics. How can we talk about how a program in a particular language is interpreted? So here we will see we refer not only to the dynamic semantics, what happens at runtime, but also the static semantics. How do we reason about a program statically, and in particular the types in a language? What makes a program type safe, and if a program is type safe, how do we interpret it? Through the history of programming languages, we see that there are different generations. So there are so-called first-generation languages, which focused on machine code. There are so-called second-generation languages which introduced symbolic assemblers that made programs more human-readable. And then a big leap came in the 1950s with third-generation languages, where we have machine-independent imperative languages starting with Fortran. The fourth generation started appearing in the 1960s, and you can think of these as more domain-specific languages, initially domain-specific application generators, and more recently different kinds of domain-specific languages. Fifth generation appeared in the 1980s. These were artificial intelligence languages, and I would say that nowadays we're moving back and forth between the third, fourth, and fifth generations. Each of these generations attempts to achieve a higher level of abstraction, but in actual fact we are still mostly at the third and fourth generations. Now we can ask the question, what actually are the differences between different programming languages? As we'll see, most languages have some common constructs. Pretty much every language has some basic data types, numbers and strings, booleans, and so on. Most languages have variables or some version of variables. You can write expressions, arithmetic expressions. You can write statements, typically, in most programming languages. Most languages have reserved keywords and different kinds of control constructs, like if-then-elses and while loops and so on. Most languages have procedures or methods or something like that. We'll see that in logic programming languages it's a little bit different, but it's not that much different. All programming languages pretty much support some form of comments that are not interpreted, are mainly for humans to read, and they have some form of error handling. If we dig a little deeper, we'll see that there are differences between programming languages too. There are languages that have type declarations and those that don't. There are languages that have very unusual and special kinds of types, like arrays and matrices and so on. There are languages which focus purely on sequential execution, and others that have specialized support for concurrency. Modern languages mostly have some form of packaging or modules. Very many modern languages are either object-oriented or they support some form of object-oriented programming. And some, but not all languages, actually very few, mostly functional languages, support very general functions that can take pretty much anything as an argument. Some languages, many of them, support some form of generics, as we'll see. And most languages support modifiable state, but in some languages, as we'll see in functional programming, you in fact write programs that don't modify state at all. So there are quite a few areas in which languages can be distinguished from each other. Now, what's a programming paradigm? I mentioned several of them already. So the thesis of this course is that a programming language is a problem-solving tool. With the imperative style that we know from languages like Fortran and C, you think of programs as consisting of algorithms and data. So they're good for decomposing complex algorithms into smaller algorithms. There's a functional style where instead of thinking in terms of algorithms, you think more specifically of functions. And with a pure functional style, you have no state change, so that makes it much easier to reason about what a function does. You think of it in terms of its input and output characteristics rather than on any state that it may modify. There's a logic programming style where programs consist not of functions and algorithms, but they consist of facts and rules. Of course, we can map these concepts back to data and algorithms, but the way we think about programs and the way we write programs is fundamentally different. As we'll see, logic programming languages have searching built into them, so they're actually good for any search style of problems. The object-oriented style breaks programs into objects that send messages to each other at runtimes, and statically we organize programs in terms of classes and inheritance. This turns out to be very good for modeling and bringing programs much closer to the concepts that we want to model from the application domains. There are lots of other styles and paradigms, of Blackboard style, pipes and filters, and so on, but we'll be concentrating in this course on the key concepts, the key paradigms that have been most popular in the last 50 or 60 years. Now, this course is about programming languages, and it's specifically not about compilers and interpreters, although we will build some very simple interpreters in the context of this course. So we won't be getting into much of the details of the implementation of the programming languages. However, it's worthwhile having a look at this slide at least once in the course. A program, as we see, starts out, so the yellow things are the artifacts and the ellipses are the processes. A program may be pre-processed, like is the case in C and C++, to expand macros and so on. Then a program ends up being parsed using parser technology to develop some kind of intermediate representation, which might be an abstract syntax tree, or it might take some other form. At that point, several things may happen. You may take the parse tree and directly interpret it, so you have a program called an interpreter, which takes this now structured form of the program and executes it directly. You may have a translator, which takes that parse tree, reads it, and then spits out a program in another programming language. This is usually a fast track when you're developing a new programming language. That was the case for many languages that I know of. For example, the first implementation of C++, C with classes, was a translator, as was the first implementation of Eiffel. And these translators simply translated the program to a new program, which is a straightforward C program, for which compilers already existed. So this is a fast track for implementing a new programming language. It has its downsides as well, however. A more common path we see on the top, we can take this parse tree and pass it through a code generator. Typically there are several other phases that have to that take place here, but ultimately the code generator will produce assembly code, which is then passed to an assembler, and executable machine code is then generated. So this is the usual path for classical languages like C, C++, Fortran, Pascal, and so on. Starting from in the 1960s, there's also another path that's taken that we see on the bottom right. You can take that parse tree and, again, through multiple phases, eventually generate some bytecode. This bytecode, then, is something which is very similar to assembler code or machine code, except it's independent of some underlying hardware. So it's essentially kind of a virtual machine language. And then a bytecode interpreter is a language that pretends to be a machine. It's essentially a virtual machine that will read that bytecode and execute the program for you. There's also another path that can be integrated into that. You may, at runtime, analyze your programs, figure out which bits of code are being run more frequently, and pass them through a so-called just-in-time or JIT compiler, which will eventually generate machine code to make those bits run even faster. So the bytecode interpretation in virtual machines we see in many modern languages, starting with languages like Lisp and Smalltalk, and progressing through a lot of modern so-called scripting languages like Python and Perl and Ruby and so on. Now, in the history of programming languages, there have been a crazy number of languages that have been developed. Here's a very, very brief chronology starting from the early 1950s. So the first major language that was developed then was Fortran. That was a huge effort, as we'll see in a few minutes. The successor to Fortran, Algol, has been extremely influential. It was the first modern imperative language. Then still, end of the 50s, we see languages like Lisp and COBOL. So the introduction of interactive programming and also business programming. We see languages like APL, which are very mathematically oriented, and languages like Simula, which build on Algol to add objects and classes. Languages like BASIC and PL01 continued these trends in the 1960s. ISWIM was a paper designed for a language, a proposal, and introduced the notions of modern functional programming languages. Then starting around 1970, we see a lot of new important languages coming out, particularly Prolog, which introduced logic programming, C, which introduced really the systems programming language, heavily in use still today. Underneath the implementation of any programming language, if you dig deep enough, in almost all cases you will find C. Pascal and Scheme were introduced in the 70s. Communicating sequential processes introduced new approaches to concurrency, which also influenced other programming languages. And then new ideas started appearing for functional programming languages like FP. Smalltalk 80, the first pure object-oriented language, was invented in 1983, and Ada was also introduced around that time in the early 1980s. Standard ML became a mainstream functional programming language, and in the 1980s we saw dozens of new object-oriented languages appearing, such as C++ and Eiffel and Objective-C. CLOS added objects to Common Lisp. Oberon and Mathematica all had their different innovations. Mathematica in particular was and still is a very influential language for writing for scientific programming. Haskell was introduced at the end of the 80s as a rethinking and merge of existing functional programming language concepts, and end of the 1980s, early 1990s, we see the emergence of dozens of different scripting languages. The most famous ones are still around today. And in the mid-90s, Java was introduced as the object-oriented language for the internet. It ended up not being quite that, but somehow that. And then C# was essentially a fork of Java introduced by Microsoft. Since then, there have been quite a few other languages like Scala and Rust and Swift. They're building on many of the concepts that we've seen so far, mainly building on object-oriented and functional programming languages, and introducing new notions of type systems. And we'll learn more about that in the lecture on type systems. Now, for the rest of this lecture, I'm going to dive into many of the languages we see listed here and just have a quick look at what were the main innovations that each of these languages brought to us. Fortran was the first high-level third-generation language. The project was introduced by John Backus, who had the crazy idea of having a system that would allow you to translate code written in a high-level language that resembled mathematical notation, and from that generate assembly code. Of course, nobody had designed such a language before, so they essentially made it up as they went along. A lot of effort was spent on how to generate code and how to optimize it. Fortran introduced symbolic notation for subroutines and functions, assignment of complex expressions. This was a major innovation. So before, with assembler code and machine code, every single statement was a single operation. With complex expressions, you could have a complex mathematical formula in a single statement or line of code, and this would expand to multiple assembly code operations. Fortran introduced do loops and comments and machine independence and input-output formats. It was very easy to learn, high level, was pushed by IBM, and was extremely successful in the scientific computing community. Here's a Hello World program. You can recognize it. So you can see here that already something like a do loop is going to be something much more high level than you would have in machine code or assembly code. Now, after the Fortran project, a committee of the programming language experts, many of whom were involved in the Fortran project, decided, okay, now after that experience, we would like to design a universal machine-independent algorithmic language. Having learned from the experience with Fortran, they now knew how to do it right. One of the key innovations of ALGOL is the Backus-Naur form, which is more or less the standard way now to define syntax for programming languages. There's a rule-based approach for defining the syntax of individual terms and expressions in your programming language. ALGOL was the first block-structured language. Now, most programming languages are block-structured. Variables have local rather than global scope. We have structured control statements. A major innovation was recursive procedures. In Fortran, that was not originally the case, and variable-sized arrays. ALGOL, its greatest success was that it was highly influential on the design of further programming languages, but it never ever displaced Fortran, and Fortran continued to be used for many, many years in the scientific community. Only recently has Fortran been pushed to the side, mainly in favor of Python. Here's a Hello World program in a version of ALGOL. Another famous and hugely important programming language from that time period is COBOL. It was designed by a committee of American computer manufacturers, and the idea was to have a programming language that not only targeted business applications, but it was supposed to be readable by managers. In fact, that was the language ended up being extremely verbose, and I don't think it ever achieved this goal of being readable by non-programmers. Nevertheless, COBOL introduced quite a few innovations, particularly separate descriptions of environment, data, and processes, and a fairly advanced module and packaging system. As we can see here, the US Department of Defense has had an extremely important influence on the evolution of programming languages, mainly because it's one of the major funding organizations in the United States, and at several points in time it made an extremely large push in funding of programs to push certain programming languages. COBOL was a very stable standard for many years and was the most widely used programming language for business applications until some years ago. I can't even begin to read this. So this is Hello World in COBOL. I don't know if this is serious or if it's a joke, but this is much more than I would have to expect to have to write a Hello World program in any programming language. PL01 was another important language developed in the 1960s and was pushed by IBM. It was intended as a general-purpose language for a large variety of different applications. Its key innovations were support for concurrency and exception handling. It was and still is considered to be the first complete general-purpose language. Interestingly, PL1 is still used in certain niche domains. Hello World in PL1 is definitely more readable than in COBOL, but it's not as elegant as it could be. In the 1960s, we started to see the emergence of functional programming languages. It was a landmark paper by Peter Landon in 1966. It was paper design, and he called the language ISWIM, or If You See What I Mean. And if you go back and read that paper, you will find a lot of ideas that have influenced heavily the design of modern programming languages. About 10 years later, John Backus, the same John Backus from Fortran and Algol and Backus Nauerform, in his Turing Award lecture also made a similar proposal to Landon's, and in this case the language FP has been implemented and incorporates many of the ideas we see in modern languages like Haskell. Also in the 1970s, ML, which stands for Meta Language, was a language implemented at the University of Edinburgh. It was initially designed as a meta language for a theorem proving system. As it turned out, as is very often the case, when you start designing a little language which is intended to solve a small problem, and then you keep adding features to it, eventually it becomes a full-grown programming language. And this is exactly what happened to ML. One of the key innovations of ML is the Hindley-Milner type inference system, which we'll see in a couple of lectures from now. This is one of the key innovations in type systems, which allows you to write a program without any type annotations, and the type inference system will figure out and guess for well-formed programs what the type should be. This allows you to write programs in a much more compact style, yet still be sure that the programs are type correct. Around about this time, late 1970s, Miranda started to appear, and in the late 1980s, a project called Haskell was proposed to try and bring together the threads from many different programming languages. Miranda introduced the idea of pure functional programming, so a functional language without any side effects, unlike ML, and this works with the help of so-called lazy evaluation. We'll see that in detail in a couple of weeks. Now, this is truly elegant. In functional languages, an Hello World program usually looks as simple as a single line, and this is the case here. Moving on to logic programming, Prolog was invented in the early 1970s in collaboration between the University of Marseille and the University of Edinburgh. Its key innovation is that of providing a paradigm for theorem proving. Programs, instead of being broken down into data and algorithms, consist of facts and rules, and to execute a program you pose a question. The fundamental execution paradigm is that of computation by unification. So if you've never programmed in Prolog before or seen Prolog before, it will be a mind-opening experience. So we'll be seeing Prolog in some detail near the end of this course. Prolog has been used very heavily in the artificial intelligence domain, in particular for developing so-called expert systems. It's also been used as a general-purpose programming language. As we've seen, once you start adding features to languages, they end up being as powerful as any other programming language. It also was used at the end of the 1980s in a huge funding program by the Japanese government called the Japanese Fifth Generation Initiative. There was a lot of interest late 80s, early 90s in Prolog. However, it never managed to fulfill the dreams, and Prolog has become less and less used in practice in the time since then. Prolog, nevertheless, is still an important programming language, still used quite heavily in certain niche domains. Here's a very unusual Hello World program, as we can see in this example. So here, hello is a question that we might ask, and in order to ask this question, we need to prove the statement on the right-hand side, which is print string hello world. And here we have a bunch of facts and rules that will allow us to establish whether print string hello world can be achieved or not. We'll see near the end of the course how this actually works. Object-oriented languages were invented very early on in the early 1960s in Oslo by Christa Nygaard and Ole Johan Dahl. They were building various simulation programs and were frustrated by Algol 60, which was the language they were using, and they felt the need for additional features to help them model real-world objects for the simulation programs. So they were motivated by the need to model real-world entities. So they added classes and inheritance to Algol. Simula, nevertheless, was an object-oriented language only by extension. So it had as a core a third-generation imperative language, Algol, with object-oriented features added on top, much as C++ was developed in the same spirit. Smalltalk, on the other hand, was developed at Xerox PARC starting around 1970, and there the vision by Alan Kay was in order to develop the next generation of graphic workstations, he believed it was necessary to have not just an object-oriented language, but an object-oriented system that would be 100% object-oriented all the way down to the hardware. The key innovations of object-oriented languages, of course, encapsulation and inheritance. The Smalltalk project really pioneered object-oriented user interfaces. They were the first graphical workstations with windows and mouse interfaces, and they started to having a huge commercial impact starting in the early 1980s. In the 1980s, countless new object-oriented languages were developed, starting with C++, Smalltalk C++, Objective-C, Eiffel, and many, many others. Interactive languages started being developed already in the early 1960s. Lisp was the first of these. A few years later, still in the early 1960s, BASIC was developed. It was developed essentially as a very simple, high-level language which would allow you to directly interact with the operating system. So there were many operating system commands which were built directly into the language. The language was very simple, which made it quite easy for new users to learn about. APL, which stands for A Programming Language, was also developed in the early 1960s by Ken Iverson as a language for concisely describing numerical algorithms. It had a large non-standard alphabet, including many Greek characters, and the primitive objects, interestingly, are arrays. If you look at this language, if you know Mathematica, has a lot of affinity with Mathematica. Mathematica, of course, came many, many years later. APL is operator-driven, so you have many simple operators, often consisting of a single Greek character. For example, iota The iota 10 generates the array of numbers from 1 to 10. There's no operator precedence. Everything is parsed from right to left. And because the language is so concise, it has a reputation of being a write-only language. So that a program that you write this week, if you look at it a week later, might be very, very hard to read and understand. On the other hand, the language being very concise, I would say that the Hello World program in APL is probably the simplest. There we see it in the bottom right corner. Many special-purpose languages were developed over the years. One very influential one was called Snowball. It was the first successful string manipulation language. In the end, it influenced the design of text editors more than other programming languages. If you want to compare it to a more modern language, think of Perl. Perl was designed as a scripting language with a lot of features to support explicitly manipulation and editing of text within a program. So Snowball also had such string operations like pattern matching and substitution. As far as I know, the Snowball has not been used in many years and has been completely replaced by languages like Perl. I mentioned Lisp very briefly. It's an interactive language, but it's also the first symbolic language. It was developed around 1960 by John McCarthy. It performs computations on symbolic expressions. The basic data structure is that of a list. So a list, as we see in the bottom right-hand corner, is surrounded by round parentheses and consists of a sequence of terms within it. Lisp may be hierarchically structured as well. So here we see in the sample program a list containing other lists. We have a small set of constructor-selector operations to create and manipulate lists. Lisp also tends towards functional rather than imperative programming. In particular, you tend to program in terms of functions and with the help of recursion rather than iteration. But the key innovation in Lisp is that there is no distinction between data and programs. Look again at the bottom right-hand corner. It's Hello World. It's a list, but it's also a function. So the list contains as its first argument, the first element in the list is the operator. In this case, it's defun, which will define a new function called Hello World. It takes 0 parameters, hence Hello World is followed by an empty list, and its body is the list that follows. It does a print of the list containing the strings hello and world. It was the first programming language to implement storage management by garbage collection. This was hugely influential over the years. It took many, many years to catch up, but eventually, starting in the 1970s with Smalltalk, and especially mid to late 80s with scripting languages, and in 90s languages like Java that run on a virtual machine, they heavily rely on garbage collection to manage memory. There's a strong affinity between Lisp and the lambda calculus, which we will see in a couple of weeks. Now, we've seen first, second, and third generation languages. Fourth generation languages are languages which are supposed to be higher level than third generation languages. Instead of describing your programs in terms of algorithms that say explicitly what you want to do, you have a problem-oriented language where you express your programs in much higher level terms. As an example, think of SQL. So SQL is a special problem-oriented language for relational databases, and when you express a query in SQL, you don't actually have to think under the hood what exactly SQL is doing in order to figure out how to resolve that query. So there's a lot of work that's going on under the hood in terms of making use of various indices and efficient algorithms to look up values from the database and produce this result. Fourth generation languages are all like that. They're very high level languages for specific domains. The first one is something called Report Program Generator for generating reports, obviously. And there were also many fourth generation systems, so not a clear boundary between a language and a system, so-called application generators. So these were very often systems that included perhaps a bit of a language, but also a graphical user interface for configuring and generating automatically an application. Yeah, well, here's Hello World in RPG. I don't even know how to begin to read it, so let's just skip that particular slide. On the other hand, SQL, even being a dedicated language for posing queries to relational databases, is not really intended as a general purpose language. However, you can shoehorn a Hello World into SQL, if you will, in a variety of ways. Here's one example. I mentioned scripting languages a couple of times. There are a number of terms which are somehow overlapping. Scripting languages, shell languages, command languages. So essentially the BASIC was a kind of a command language rather than a scripting language. It was a language for directly interacting with the operating system. Shell languages as well, like shell for the Unix operating system, is also a cross between a programming language and a language allowing you to directly talk to the operating system. So the Unix shell, invented by Bourne around 1971, was developed both as a user shell but also as a scripting tool. What we mean by scripting tool, essentially the idea of a scripting tool is that a tool will take existing components and combine them together to develop a complete program. So this is the case as well with the Unix shell. You can use the shell to write a script, so a textual program, which when executed makes use of various compiled C programs in order to produce a result. HyperTalk is an example of such a scripting language at Apple, used to script applications made as so-called hypercard stacks. TCL, or Tickle, in 1990, it was developed as an embedding language and a scripting language for X Windows. It was very popular, especially in the 90s, but I haven't heard of it being used in recent years. Perl, I've also mentioned. It started out as a text manipulation language in the 1980s, but when the internet and the World Wide Web started taking off in the early to mid-90s, then Perl ended up being very quickly seen as a very nice way of quickly developing dynamic web pages, because Perl was able to manipulate text and generate HTML on the fly. Scripting languages have introduced numerous innovations. In the Unix shell in particular is the paradigm of pipes and filters, which are very, very efficient. So with the Unix pipes and filters chain, you can take a sequence of Unix program, each of which takes input and produces output for the next stage in the pipes and filters chain. Tickle, on the other hand, was very successful as a high-level language for developing very quickly user interfaces as scripts. There's a long list of successful scripting languages over the years that have been very popular for solving a variety of different problems. Slowly summing up, where have we been? Where are we going? In the early days of programming language design, there was a lot of emphasis on static languages where you have to explicitly specify the types of all variables and functions and procedures so that the compiler could use this information to generate very, very efficient code. Since computers became faster and cheaper and smaller starting in the late 70s through to the mid 80s and beyond. People realized that the most expensive resource was no longer the computer, but the programmer. So there was a lot of new interest in developing languages that were perhaps more expensive to run, but much easier to program in. So there was a lot of interest in dynamic languages, scripting languages, so-called domain-specific languages, visual languages, and since the mid to late 90s in modeling languages. So these are all directions where we can expect future developments. That concludes the lecture today. I'd just like to point out that at the end of each slide deck, there are 2 additional slides. One which is titled What You Should Know. These are some hints to you after listening to the podcast or reading the lecture slides. You should be able to easily answer any of these questions. In addition, there's a slide that asks, can you answer these questions? And these are more thinking exercises. So you may not find the answer to these questions in the slides themselves, but they're starting points for further thinking or further research or further reading. And both of the slides should help you to study as well for the final exam, to give you confidence that you have all of the material under control. Finally, all of these lectures are available under Creative Commons license, and you're free to reuse these materials according to the Creative Commons Share Alike 4 license. Thanks very much for your attention.